Hello, Calc. How you doing? We're come to that point where we are pretty much done with derivatives, although they're not going to go away. They will still be in our work very often, so we're not going to forget about them. But we're at the second half of calculus, and that's where we're going to learn about integration. So the integral is a new sign. The integral, it looks like that, sort of a curvy, almost S, a skinny S. And the integral is what indicates an integration is taking place. Another way to say an integral is an antiderivative. So let's think of it in that way. An antiderivative is like what its name indicates. It's the derivative in reverse. So we're going to reverse some of the rules that we learned with derivatives and they become integrals. So for example, say we have y equals x squared. The derivative was 2x. So what we're going to do this time is we're going to say the integral of 2x, and I add a little term, I'll call it, a little symbol, and that's called dx, and that tells the reader what the variable is. So it's saying I want the integral of 2x with respect to x. So you have to have a dx if you're integrating with respect to this variable. You could integrate that with respect to y or any other variable, but we'll keep it simple this time and we'll learn about that kind of situation later. So the integral of 2x. So what expression has this as its derivative? Well, you can peek up here and see that it is x squared. However, what about the expression y equals x squared plus 2? Y prime is also 2x. So couldn't I have said, what expression has this as its derivative? Couldn't I said x squared plus 2? So it seems to be more than one answer. Couldn't it have been x squared plus 3? X squared minus 5, x squared plus 6. So the answer to that is yes. We could have lots of answers, and the way we handle that with derivatives is we say plus c, and that stands for a constant. So c could be any constant, and we've covered all of our examples that have this as its derivative. All right, so let's try another one. Let's try, without seeing the first one, can you think of what has this as its derivative? So you can probably see where that came from. Where did it come from? Well, the expression x to the third. Can you think backwards? Can you take this, find its derivative here, 3x squared, and plus c. Alright, so there are actually rules to help you, so you don't have to always think like that, think backwards like that. Notice the relationship here. This went up 1, and this 3, this 3 will be involved. So let me give you the rule and see if it makes sense having seen these two examples. So let's say that a function is given and it's x to the n. And we're going to use the power rule for antiderivatives by saying the integral of x to the n dx equals x to the n plus 1, notice that relationship, The 2 here became a 3. The 1 here became a 2. So the n here becomes an n plus 1. And it's going to be divided by n plus 1. Does that work for the integral of 3x squared? Let's see. The integral of 3x squared equals 3 times x to the 3, that's n plus 1, divided by n plus 1. And notice we get back to x to the third, which is what is the answer. So it did work. The integral of 3x squared is x to the third, which is what we expected. Oops, sorry, I'm out of the screen. Alright, so write down this rule, n plus c. I often call it, I say, and crown it. Nobody else says that, so don't try that in your future math course. But I'll say, and remember to crown it. That means put on the c. Notice this formula does not work if n equals -1. So I'm going to make that stipulation that n cannot equal -1. Alright, so now I've opened up a lot of integrals that you can take. So let's start taking them. Alright, using this rule right here, I'm going to leave that in the screen, and I want you to think, what is the integral of x to the third dx? And so, using the power rule, this is our n, so x to the n becomes x to the n plus 1 divided by n plus 1. So we get x to the fourth over 4 plus c. Let's prove to ourselves that that really is the expression that we want. And we can do that by taking the derivative of this and see if it gets back to that. So the integral will undo what the derivative does. The derivative will undo what the integral does. Sort of like addition and subtraction. So we have integration and we have differentiation. So let's say y equals 1/4 x to the fourth plus some constant. Let's take the derivative of that and see if it gets us back to where we started from. The 4 runs down in front, times 1/4, and this reduces by 1, and the constant's derivative is 0. So simplifying that, you'll see it is x cubed, which is what we started with. So you can always take an integral and check it by doing the derivative of your answer to see if you get back to the problem. Alright, so let's try another one. So again, the integral of x to the n dx is x to the n plus 1 over n plus 1 plus c. Alright, let's try it and find the integral of x to the minus 3. So using the rule, we get x to the minus 3 plus 1 divided by minus 3 plus 1 plus c. Alright, x to the minus 3 plus 1 is x to the minus 2, and this is minus 2 plus c. Alright, so we can write it like that, or we can write the x to the minus 2 in the denominator, where the exponent will be positive. I'll just leave it like that for now. What if there is no variable? This will be in our screen, so I'll do another one. The integral of 5 dx. Alright, so here, can you think of 5 times x to the 0? Anything to the 0 is 1. Now you can follow this rule when it's in this form. So I'm going to get 5. Any constant can cross the integral sign and not be affected by this rule. So this equals 5, the integral of x to the 0. Forgot my dx. Alright. So 5 comes across, and now I'm going to apply the rule to x to the 0. It becomes x to the 0 plus 1 divided by 1, and plus 1 plus c. So simplified, that's 5x plus c. take the derivative of that and see if you get 5. Indeed you do. Alright, so how good are you at thinking backwards? I think that will give us a start tomorrow. Try one more. I'm going to see if there's any others that I like to do. How about the square root of x? How can I write that in the form x to the n? Well, we certainly have done that enough this year. So we can write it as x to the 1/2. So using the power rule for integrals, this increases by 1. So we get 1.5 or 3/2 divided by 3/2 plus c. So I can write that as 2/3 x to the 3/2 plus c. When you have the integral of a sum, say we have this expression plus this expression, I would like you to know, and this is in terms of x, I would like you to know that the sum or the difference of two integrals is the integral of the sum. So the integral of a sum is the sum of the integrals. So I can break those up into two individual integrals and add them. So this one, the 3 will cross the integral sign, gives us 1 in the form of the power rule that we like, and the 2 can cross the integral sign, and now we're ready to use the power rule. 3x to the 3rd over 3, and 2x to the 2 over 2, and this would have a plus c and this would have a plus c, but we have a little trick. We don't say c plus c is 2c. We say that it's just another constant. So these are not going to follow the rules of algebra because they just represent a constant. So one constant plus another constant is just a constant. Alright, so if you integrate this, if you take the derivative of this, do we get back to the original? We get 3x squared plus 2x plus 0. We do. Alright, so a little tiny introduction to integrals, and we will add to that tomorrow night, but tomorrow you'll be practicing these basic expressions. Alright, hope you enjoyed integral calculus. More to come. Much more. Bye-bye.